So, in our last lecture, we were talking about conformation of molecules, right? So remember, we were doing the Newman projection of a ethane or a larger molecule like a butane, something like this. Remember doing the Newman projection of like this one being the highest energy conformation, and the further away these two methyl groups are away from each other, this one's the lower energy staggered conformation, and the eclipse one are higher energy, and you can rotate it to get the full energy surface. So that's last lecture. At the end of our last lecture, we also went over discussion of ring strain. Like the three-member ring is a highly strained molecule for two reasons. One is the angle strain, meaning the carbon-carbon-carbon angle is like large, it's only 60 degrees. So it's away from what sp3 carbon want to be. And for two, we have the torsional strain. Like if you look at the Newman projection of the cyclopropane, you end up seeing all the atoms are eclipsed with each other. So that's cyclopropane. It's a pretty strained molecule. So today we'll be talking about the class of molecule. They are cyclic molecule, yes, but they do not have any ring strain. So these are cyclohexanes. So on the left-hand side, we have the molecule of cyclohexane. This one I calculated using like quantum mechanical calculation softwares. And the bond angle is about 111 degrees. So it's very close to 109 degrees. And thus we say your cyclohexane doesn't have any significant ring strain. And the structure of the molecule of the cyclohexane look like this from the side point of view and look like this from the top point of view. We call this conformation, this is the lowest energy conformation of your cyclohexane. We call this a chair conformation. Whether or not you can see it as a chair, that doesn't matter. That's what conventionally called as a chair conformation. It's not like one of these chairs, it's more like a beach chair that you can like lie down on it. So if you can see it as a chair, perfect. If you cannot, don't force yourself. Just knowing the lowest energy conformation of cyclohexane is called chair conformation. So when we draw this conformation on paper, we want to make sure we're representing the chair conformation as much as possible. So this is the drawing that we typically do. Like if we look at the front one, you're sort of having a V-shaped, like going up. Let me use a different color, right? So I'm just drawing it on this molecule. So it's like a V-shaped on the top, and I can copy paste this drawing. And then on the right, we have a V-shape that's coming down. So I can copy paste this up. And then we're connecting the end of this V shape. So that's our chair conformation of the skeleton. And then you can add the hydrogens in. So in here, I put two different colors, and we'll see why we put two different colors in the chair conformation very soon. But looking at it here, we can put them as like either going like straight up or straight down. Or this one, straight up or straight down. And alternatively, you can have them pointing sort of to the side. And that's what we work in a different way. So note that for every carbon center here, you always have one hydrogen that's pointing up, the other one pointing down. Likewise, one up, one down, one up, one down. So that's when we're drawing the hydrogens on the chair conformation. And let's look at the side chain, right? Let's look at the cyclohexane from a different perspective, because we were talking about there are two different kind of ring strain in cyclopropane, namely the angle strain, and then we have the torsional strain. So in here, we went over saying the angle strength is minimized because the carbon-carbon bond angle is very similar to 109.5. What about torsional strength? So to look at torsional strength, we want to put it to our Newman projection perspective. So in here, we're just effectively looking through these two bonds. All right, so I'm just tilting this one to a point of view that is like from top down. So we're looking through these carbon-carbon bonds. And what we end up getting, now if you think about it, like this one is my front carbon. So on the right-hand side, when we're drawing the Newman projection, you have the front carbon, and this one comes out to the center CH2, and then you have two hydrogens connecting to it. Right, on the back of this carbon, we have a CH2 coming out, and then hydrogen and hydrogen. So that's from the left point of view, from this carbon here. With me so far? And likewise, from the left carbon, we can draw this ring. That's the center. And then we form a bond between this CH2 and then on the bottom to this CH2. And then we add in the hydrogens. All right. So here I'm just like drawing out my chair conformation using the Newman projection. But from this perspective, we can find out that all of our bonds are effectively staggered to each other. We do not have any eclipsed carbon-carbon bond, so that's why we say the chair conformation doesn't have any significant torsional strain. So all my bonds are staggered to each other. So now please take out, yes?
So those two Newman projections are connected?
Yeah, so these are connected via the two CH2 groups in here. Like if we look at these carbon-carbon bond here, they should be connected, right? You have a common center CH2, and then you have another CH2 on the bottom. So these two are the CH2 connecting the two carbons. All right. So please take out a piece of paper and let's just practice drawing these chair conformations together. It looks like untrivial to draw it a pretty one, but as long as you draw it correct, I don't care how ugly it is. So here are the tricks. Let's just follow it, right? So first of all, you want to draw 4 points that basically define parallel. So this is my tricks. I'm not very good at drawing it pretty, but I'm good at drawing it correctly. So let's just do 4 points that are more or less parallel with each other. And then you can draw two V-shapes. All right, so the two V-shapes are in this one. So on the top, it's like tilting down, and on the bottom, it's tilting up. Just draw two V. And then we're connecting the left two dots and the right two dots. And that's it. That's a chair. Likewise, you can draw it in a different way. Like if I'm tilting to the left instead of tilting to this wall instead of the other direction. Well, likewise, we can do a V, and then another V, and then connecting the dots. Right. It doesn't need to be the 100% perfect, pretty chair, but this drawing will give you a correct chair, if you may. And that's your chair. Yes?
I have a question on something else you said. So you said in the notes there's no torsional strain because they're staggered. So can you only say like whether there's torsional strain or not? Like you can't specify from that?
So for this one, when we say there are like no torsional strain, because they're all staggered, and so what's your question about like
Like
it is not staggered, it's no longer a chair conformation. So for example, I can like force it, I can force my molecule to be this kind of shape, where all my bonds are eclipsed over each other. I will go over it. This is what we call a boat conformation. So this is a higher energy conformation of cyclohexene. But what we can say is for the lowest energy conformation of cyclohexene, all of my bonds are staggered with each other, and thus they are more stable. That's why the chair conformation is a more stable conformation. Sorry, just dropped my microphone. Yes?
When you ask about like the lowest and highest chair conformations, are you asking about like?
No, there's no lowest and highest chair conformation at the point. We haven't added any substitution yet. So right now, these two chair conformations will have exactly the same energy. Okay, so let's just move on. So now you know how to draw the chair, especially the skeleton of the chair. And let's think about the next one. Now, as I was showing here, we have different colors of the hydrogen. So what does that mean? So what does these different colors mean? So in this case, we first want to specify an observation. It's like when you draw these two chairs in different ways, like if we start from here. Now, we have all my blue ones on the like straight up position. Oh, the other way. Let's start here. So in this case, I have all my green ones. Wait. These should be black. So assuming my black hydrogen in this drawing are my white hydrogens in this molecule, now all my blue ones are like pointing directly up or directly down. With me so far? It's like looking at the other way. It's always pointing directly up or directly down, while the green ones are pointing to the other directions. So this is one of our chair conformation. We see like it's sort of tilting to the left-hand side. And if we're doing a ring flip, because we have different way of drawing my chair, we can do a ring flip of forcing it to a different chair conformation. So now I can have my green ones all on the top, like straight up, and my white ones like on the side. So these are time we gave these two different types of hydrogen a name. So in my chair conformation, whenever you have something that's straight up, these are what we call axial. Or sometimes we write it with a little number A. And then when you have something that's pointing away to the side, we call them equatorial. Right. So if we draw it on that figure, when we draw it, we have the axial hydrogen and the equatorial hydrogen. Axial, equatorial. Axial, equatorial. Axial, equatorial. Yes.
Does it matter like when you go to like where you draw your hydrogen up, like oh it has to point up?
So in this case, when you're drawing the hydrogens, you want to make sure like when you have like something like concave up, and then you must have an axial that's pointing directly up. If you have an edge that's concaving down, you'll have an axial that's directly pointing down. With me so far? So it's like in this case, when you have like 1, 2, 3, so these 3 carbons, you have like concave up, so it's like going like a top V shape. So the axial hydrogen will always be pointing straight up. Alternatively, if you have 1, 2, 3, these 3 hydrogens are like like a normal V shape, so you'll have the axial hydrogen directly pointing down. So it's easier if you write out the axial hydrogens and then you put in the equatorial hydrogens. Yes.
So in chair configurations, there's always the same amount of axial and equatorial hydrogens?
Right, so in cyclohexane, you always have 6 axial positions and 6 equatorial positions. They don't have to be hydrogens. So when we put on different substitutions on the cyclohexene, in our next slide, we'll start to see it might make a difference.
But those are
Right.
always the same number, right?
Right, it's always 6 axial, 6 equatorial. So here, just like practice again, enjoying my axial and equatorial hydrogens. Like this one is coming down, coming up. So I'm drawing all the axial hydrogens all at once. And then the equatorial hydrogens. Right, so for every carbon, you'll always have like one up, one down, one up, one down. And when you're actually looking at the structures of the cyclohexene, when both of them are pointing up, they are cis to each other. Meaning like if we look at this bond, right? So these two are cis to each other, even if one of them is axial, the other is equatorial. So in here, we can circle, like for example, these two hydrogens are cis to each other. They're both pointing up. Or these two are cis. They're both pointing down. Yes,
In our cyclohexane, if it's not hydrogen, but it was like methyl or something?
we'll get there.
Okay.
Yeah. Yes.
Does cis only refer to if they're both axial, or do you also have?
No. So cis, trans refer to whether they're pointing up or down. So we have two sets of things describing these positions. One set is axial versus equatorial, right? So axial versus equatorial, that's one set. The other set is whether or not it's pointing up or down. So in this case, these two, one of them is axial, the other is equatorial, but they're cis to each other. We could also point to like these two hydrogens. They're both axial, but they're pointing both towards the same direction, and these two are cis to each other. So cis-trans only matters to whether it's pointing up or pointing down. And then axial equatorial refer to whether it's like straight or like pointing to the side. So far so good? Now, as we were saying, we have two different ways to draw the chair. Now, these two conformations can undergo a ring flip. So same like these two conformations, like the Newman projection, remember in the Newman projection, we were rotating through a single bond. For cyclohexene, the process of changing between the two conformations is called a ring flip. So the mechanism of ring flip is actually pretty complicated. So first of all, my expectation to you is you know to name and the relative stability of these less stable conformers. And secondly, know that ring flip between the two chairs will exchange equatorial versus axial hydrogens. So that's my expectation to you. And now we can look at this profile together. So don't get frightened. So what we get started. Now, in this profile, I'm just playing with this molecule. One minute. Okay. So we'll start from one of the chair conformations. So bear with me, just focusing on this carbon here. What's going to happen is in this case, we have all of my white hydrogen pointing directly up, or my white hydrogen in the axial position. And in here, let's just focusing on this carbon. This is the one I highlighted in yellow here. And there's another red one that I highlighted in red. So looking at these two, that's where our starting point. And now, in the process of doing the ring flip, what we'll first do is keeping the red carbon not changing, but now instead of a V shape, I want to twist it so that my left one is now like on the same plane with the rest of the molecule. So this one is not changing, but this one I put it in the same plane as the rest of the molecule. So now like 1, 2, 3, like these 4 atoms is forming a plane. We're putting them on the same plane. This conformation is called a half chair. It's a high energy conformation for, well, now the atoms are eclipsed with each other if we put it on top of each other. All right. And then from the half chair, we can then twist this atom up to form what we call a twist boat. So now they're no longer eclipsed with each other, but we have like these two hydrogens very close to each other in a twist boat. So on the right, I'm keeping that red one unchanged throughout the way. I'm not changing it, I'm holding it in my hand. So the twist boat is slightly lower in energy, and then eventually will form a boat conformation, so that the bottom four are coplanar, and the top two are like pointing towards each other. So that's what we call a boat conformation. And then we can hold this yellow one unchanged, and then twist the red one to become a twist boat and then a half chair. All right. And then from here, we'll twist it back so that we have the lower energy conformation of chair conformation again. Yes.
Could you show it from the side so we can see?
Okay, so let's see. I'll start again. Now I'm going backwards. Okay. So on here, this is where we start from. This is the red carbon on my hand. This is my red carbon, and this is the yellow carbon. With me so far? So now let me just hold that yellow carbon unchanged. I'm gonna force it into my half chair conformation. So I'm just so to the side. Okay. So this is the side. So that's my red. This is my yellow. So I'm just forcing it to an eclipse high energy conformation, so that this one is forced to be eclipsed with its neighbor. And we can put it into the boat so that it's not staggered again, but just in a different way. All right. And then putting the other one back, we get back to our other chair conformation. So you see the difference between the two chair conformation is switching all of my equatorial position with all of my axial position. So in this case, we started from my white one being my axial hydrogen. And then throughout the ring flip, we're like forcing it to change to the green one being the all axial position. So that's the most important take-home message. So two things in the ring flip mechanism, really. One thing is knowing that the ring flip mechanism takes place via a series of high energy intermediate or less stable conformations. These are called half chair, twisted boat conformations. So the ring flip takes place via the series of high energy conformations. And then knowing what comes out from the ring flip. The ring flip switch the position of your axial and equatorial positions, whether it's hydrogen or something else. Yes?
Would you be expected to draw twisted boats?
No. I don't expect you to draw twisted boat. I don't expect you to draw boat conformation. But if in a multiple choice, I can give you, like say, a chair conformation and maybe like a boat conformation, you can tell me which one is higher in energy. Yes.
How similar in concept will exam questions be to worksheet questions?
Very similar. Well, I make your worksheet problem. I make your exam question. I'm the same person. Yes.
What about the online called the extra credit stuff? Those questions, are those helpful in that sense, or?
We have to chat about it after class, but I don't know what exactly is the online resources you're talking about, so I can't comment directly. All right, one more question.
Can you show if I can get from chair to half chair again?
So from chair to half chair, you're just holding one of this one unchanged, and the other one you force it into the same plane with the rest of the molecule. So it's like you keep one of it like unchanged, and the other one you sort of have to force it, so that if you look at on the side, they're like eclipsed with each other. That's why the half chair is so high in energy.
The hydrogens are all eclipsed with each
Yeah, I mean, the carbons are basically like, if you look at it on the side, they're all eclipsed over each other. Okay. And this is the ring flip. So the ring flip of cyclohexene itself was all hydrogen. It's a little bit boring because the energy is the same in both of your conformations. But when we start to talk about substituted cyclohexene, things will become more, I don't want to say interesting, but things will become more significant, especially the conformation of your chair becomes more important. So if we look at some situation here, let's just do an example. Imagine I now replace one of my hydrogen with a methyl group. Okay, so I'm replacing one of my hydrogen with a methyl group. So likewise, we still have a chair conformation. Now it's a substituted chair. So how should we draw it? Now on the left-hand side, remember we draw like the 4 dots. And then you're connecting them with a V on the top, and then a V on the bottom. All right, and then looking at where my methyl group is, that's here. And I have hydrogen, 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 axial, equatorial, axial, equatorial. I'm just gonna add my highlight of green one, green one, green, 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 green. All right, so basically just drawing out from that structure. We know that the white hydrogens are axial because they were directly pointing up. What, yes?
The equatorial hydrogens like always like form like the tetrahedral shape.
So all the carbon center are still tetrahedral shaped. So that's why we always have like one axial, one equatorial. Now, if we look at the same molecule from the Newman projection perspective, so now thinking about it, we're looking through this chemical bond so that my methyl group is on the right-hand side of my Newman projection. What do we have? So writing it out, this is the same conformation. The chemical bond I'm looking through is like here. And that's my little I. And we're looking through those 2 chemical bonds. And what does that look like? On the right-hand side, we have a Newman projection, and that's my CH3. And connecting to this center carbon, that's my CH2, and then the hydrogen. Right, on the back, we're connecting it to CH2, hydrogen, hydrogen. And on the other hand, we have our another cycle of Newman projection coming out. So something like this. All right. So looking at this conformation, we see this methyl group in the equatorial position is pointing away from any other groups. So it's like very away from any other groups. So this is where my methyl in the equatorial position. And what about, let's do the ring flip right now. Remember, in the ring flip, we're switching the position of my axial and equatorial groups. So that means I'm just gonna twist it up so that we have my methyl group in the axial position. All right, so if I draw it out, what does that look like? So if we're doing it this way, we end up getting, well, another ring tilted to another direction. And we do the V shape. And then you put in Well, my CH3 is in the axial position, and then I add all my other hydrogens. Now all my green hydrogens are in the axial position. And then my white hydrogens are in my equatorial position. So far, so good? Like the ring flip basically just switches the position of your axial and equatorial positions. And what about the Newman projection? Now, I'm looking through this chemical bond here. Again, the two chemical bonds I'm looking through are here. So in the exam, I might ask you, like I give you to which bond you're looking through. Can you redraw that chair conformation into a Newman projection? And what does that Newman projection look like? Well, on the right-hand side, we have my methyl to the bottom, and then the hydrogen, and then we have a CH2 connecting it. And on the bottom, we have CH2, hydrogen, hydrogen. And on the left-hand side, again, we're connecting the dots. With me so far? So we're just writing out the Newman projection of the chair conformation of my methyl cyclohexene with the methyl group on the axial position. Now if we look at our Newman projection also on the molecular kit, we see that this methyl group is in very close proximity with like this hydrogen, or it's called the Wang-3, with these two hydrogens actually. So this is what we call a Wang-3 diaxial steric repulsion. So in here, we have this one. These two are undergo very high steric, not very high, but somewhat high Wang-3 diaxial steric repulsion. And this little symbol just tells you they don't like to be too close to each other. There's like a steric clash between these two groups. If we put it on the chair conformation, what we're saying is there's a steric clash between this one. And it's called Wang-3. It's like from here, you count 1, 2, 3, or 1, 2, 3. So like if you count like 1, if you assign this group to be 1, and then you count like what's the number 3, like 1 carbon away. So these are the steric repulsion between the circled axial groups. Take-home message here is whenever you have a substituted cyclohexane, you want to put the sterically Bacchier group on the equatorial position, not on the axial position. The more group you have on the axial position, the less stable that ring conformation is. Any questions? And let's do an example question together. One of the things we can ask you to do is, can you draw the most and least stable chair conformation of your trans 1,4-dimethyl cyclohexane? All right, so this is as much as nomenclature go. Like if I tell you this is a 1,4 trans dimethyl cyclohexane, you know what kind of molecule to draw on paper. And what are the chair conformation that we want? So let's start from somewhere. Let's start from here. Again, we draw our chair skeleton first. And we think about our 1,4, where are they? 1, 2, 3, 4, 5, 6. Now I want to put my methyl group on equatorial position. So I put my methyl group on equatorial, and 1, 2, 3, 4, and this one, I also can put it on equatorial. And double check, are they trans to each other? Now this one pointing down, this one pointing up, so they are equatorial to each other. They are both equatorial and they are trans to each other. So we're happy. All right, so this one is our lowest energy conformation. Yes?
Does it matter where you start counting?
It doesn't matter where you start. I just choose to start somewhere. Like you can also start here, like, well, I can just start somewhere else. Okay, so what if I start counting maybe 1, 2, 3, 4, 5, 6, and I can put this one as equatorial, and this one is also equatorial. They're all correct. It doesn't matter where you start. Yes.
So, would it be possible to draw a cis for this since it's 1, 4, and would it hurt?
Well, if it is cis, now you think about it, you want to have them pointing towards the same direction, both pointing down or both pointing up. So in this case, if it is cis, then one of them must be a axial position. Then it doesn't matter which one is highest or lowest, they all have the same energy. So cis trans matters when you are putting the direction of that bond, whether it's pointing up or pointing down. And the axial equatorial means whether it's straight or it's like to the side. Now this is the lowest energy conformation. What about the highest energy conformation? So for the highest energy conformation, we're putting them on the axial position. I'm just draw another chair. Again, I don't draw, very pretty chair, but at least they're correct. So 1, 2, 3, 4. Now I have a axial methyl, and on the 4, I have another axial methyl, and they are axial. They're all both axial, thus they are less stable. And the reason they're less stable is because of the 1,3 diaxial repulsion. Yes.
So if the question has like cis 1, 4, and you say high or low energy, it's going to be the same?
Yes. So in this question, if we're asking for a cis 1,4 dimethylcyclohexane, then all of the both of the conformation will have the same energy because you inevitably have one equatorial, one axial. Yes.
So why is the axial least stable? Because if you're looking at it like a Newman projection, down that way, then those would be not.
Right, so if you think about it, this one is again, the question here is why is the axial methyl group making the ring conformation less stable? Now, if we look at this one is having the methyl group on the axial position. And you look at the distance between this methyl group to the other axial hydrogens that's on the same phase with each other. Like this one is in very close proximity with these two green hydrogens. On the side, it might be more obvious, like it's directly pointing towards these hydrogens. Okay, and let's do the ring flip together and putting the methyl group on the equatorial position. And that's what it looks like. And now when putting the methyl group in the equatorial position, now we can see this methyl group is way away from the other groups. So another extension of the question is now let's say I have methyl versus isopropyl and it's cis, right? So maybe we can say like cis. What if we want to draw the conformation, the lowest energy conformation of a cis? One methyl, one isopropyl, 4 methyl cyclohexane. Right, so we have, say, a isopropyl group here, and then a methyl group. Now, isopropyl group itself is like the one with like a carbon attached to 2 other And then my methyl group can be in the axial position. So this one will be lower in energy. Alternatively, if I put my isopropyl group on the axial position, 1, 2, 3, 4, and then I put my methyl group on the equatorial position, this will be higher in energy. Yes.
Wait, is it because you're following the isopropyl group and because it's like bigger and it's?
Yes, so the isopropyl group is bigger, right? So we want to avoid putting the isopropyl group on the axial position as much as possible.
So like the methyl group being in the axial position. Like,
Well, it's not ideal, but we have to put it somewhere,
Yeah.
right? It is cis to the isopropyl, so it must be in the axial position.
So the most like lowest in energy that they're both on the equatorial.
But you cannot do that for a cis 1,4 isomer because they're cis, they're pointing up, right? So the bottom line is before thinking about putting everything on the equatorial, thinking about the cis and trans and putting them in the right direction, on the right carbon. And then think about, okay, can we put them both in equatorial? If not, I can put the larger group on the equatorial. Okay, any other questions on chair conformation? Yes?
Sorry, so, just confirming on that one, so because isopropyl is bigger and it's in, equatorial,
Mm-hmm.
and the other one's in axial, it's lower in energy.
Yeah, because now we're comparing isopropyl versus methyl, right? So isopropyl is bigger than methyl. If one of them must be in axial, we put the methyl in axial. Okay, and then we have about 5 minutes left. We'll quickly finish up our chapter 2 on physical properties of alkenes and cycloalkenes. So typically, alkenes themselves are pretty chemically inert molecule. Like in chemistry, you don't do too much reaction with normal alkenes. So that's why when you write like an R group, you typically assume it's just some kind of alkene group that doesn't react with the rest of your molecule. So when we're thinking about why they're like not so reactive, chemically speaking, is that my CH bond and CC bonds, they're typically nonpolar. They're covalent bond, they're nonpolar. Their electronegativity is very similar to each other. So when we're looking at alkenes, we only thinking about very weak, non-covalent, like London dispersion forces will exist between these alkene molecules. For physical properties like boiling point, melting point, or density, when we're looking at alkenes, well, larger linear alkenes will tend to have larger or higher melting point, boiling point, and density. So the longer the chain is, the higher the melting point, the boiling point, and also density it will be. The other thing to keep in mind is we went over constitutional isomers, right? So constitutional isomers, you draw your alkane in different ways, but with different connectivity. Now, depending on the constitutional isomer, depending on the connectivity of your atom, they might have different physical properties. So for example, when we have like a linear butane, the boiling point is like -0.5, and when you have the more branched methylpropane, and that's boiling point is like -11.6. So your linear molecule have higher boiling point than your branched molecules. And when we're talking about reaction of alkanes, it's really pretty boring if you think about it. It's just like in this class, at least, we're only talking about combustion of your alkane. It's just you put your alkane with oxygen, you burn it, you get water and carbon dioxide out from it, and know how to balance that chemical reaction. You can also calculate the heat of combustion, which is the amount of energy released for that combustion reaction. So that's the that's how you get heat, by burning fuel. And we're gonna formally introduce chirality in our next lecture, but since we have like 4 minutes left, I'm just gonna quickly go over the concept of basic chirality. Chirality is something that people feel it's like super frightening when they look at organic chemistry. But here is the thing, like, okay, first of all, next lecture, if you have, please bring in some molecular kit. At least you'll need like something like this, like 2 molecules that are sort of, you can play around with it. So next lecture, if you have one, please bring in your molecular kit. You don't need the entire kit, you just need a few molecules. That's one. Secondly, next lecture we'll be talking about chirality with different kind of chirality and different kind of symmetry plane. The very straightforward introduction to chirality is just looking at our hand. So your left hand and your right hand, you cannot superimpose them on top of each other. You can only do mirror image with your left and right hand. The same applies to molecules. Now these 2 molecules, we cannot superimpose them with each other. Like, for example, if I put my blue one here and my white one here, like my red and black one will always be switched in position. So that's why we say these 2 molecules, they are chiral molecules. They're different stereoisomers with each other. We'll go over them more detail in the next lecture, but just a reminder, bring your molecule. In our next lecture, we'll look at these molecules together and give chirality a nice and easy definition. Okay, I'll see you next week.